Assalamualaikum and greetings. My name is Muhammad Muaz bin Jamain and we are from Group 10. We present to you our group project that named Weapon Detection with YOLOv8. And this our group member, which is consists of Alfan Alfa bin Nandri, Muhammad Faris bin Rosli, Muhammad Alif bin Yusni, and myself Muhammad Muaz bin Jamain. The content that we will explain in this presentation is introduction, objective, problem background, related research, methodology, dataset, result and discussion, and finally, conclusion. For introduction for our project, which is weapon detection with YOLOv8, technology has revolutionized surveillance system, shifting from human-operated monitoring to automated solution with AI and machine learning. Traditional method limited by human error and insufficient for modern security needed, especially in crowded public spaces. And AI-based surveillance excel in detecting firearms in places like airport and school, where detection methods struggle with large data volume. Among AI models, YOLO, which is you only look once, is known for its efficiency and accuracy in real-time object detection. The latest version, which is YOLOv8, improved performance with advanced features, making it ideal for weapon detection. Integrating YOLOv8 in surveillance system enhance security by providing accurate real-time firearm detection, reducing human error and enable quick threat response. This research focused on development and effectiveness of YOLOv8 for weapon detection, underscoring its importance in modern surveillance.
And now for the objectives of our project is like to identify and analyze requirements for the weapon detection system, including weapon types, operational environment, and performance criteria, and to design the system architecture using YOLOv8, covering data processing, model training, and integration with the existing surveillance systems, and to evaluate and testing and validate the system to ensure the accurateness detections and classifications of weapons, image and video streams, enabling faster threat responses. With the increasing frequency of security threats, there is a critical need for automated systems that are capable of detecting weapons in real time. With the traditional security measures are now often insufficient due to their reliance on manual monitoring, which is both time-consuming and prone to errors as well. The integration of machine learning and computer vision technologies, particularly the YOLO algorithm, offers a viable solution to this problem by providing rapid and reliable weapon detection. For the related research that we have been done for this project is like the object detection research has advanced significantly with leading models like YOLO, SSD, and faster RCNN. YOLO, introduced by Redmond 2016, is known for its speed and accuracy, making it ideal for real-time applications. It treats object detection as a single regression problem, predicting bounding boxes and class probabilities from full images. SSD, presented by Liu 2016, uses a single deep neural network to predict object classes and offsets in one pass. And faster RCNN stands for faster region convolutional neural network, introduced by Rand 2015, uses a region proposal network for balanced speed and accuracy. For the latest YOLOv8 we thought about here, the iteration incorporates advanced architecture and training techniques, improving feature extractions, computational efficiency, and training methodologies. These enhancements make YOLOv8 highly effective for real-time object detection. Stated by Joe here, 2021.
Okay, so for the methodology, first we have data collection. The dataset source from Kaggle includes image of various types of weapons and is divided into training and validation sets. Second, we have data preparation, which is data loading. Images will load into the workspace for training and evaluation. And then we have data annotation. Annotated image with bounding boxes were verified for accuracy. We have class labels, classes.txt map annotation to weapon classes, and then we have configuration file, which is weapons.yaml ensured compatibility with YOLOv8. On the third, we have model selection. So YOLOv8 was chosen for its high performance in real-time object detection, featuring improved feature extraction and computational efficiency. The fourth is training. So for training, there is a setup where I configure training parameters based on YOLOv8 documentation, including batch size, learning rate, and epoch. And then we have data augmentation, where I apply techniques like random cropping, flipping, and color adjustment to enhance robustness. Last is training, which is periodically evaluated on the validation set to monitor and adjust performance. And fifth is evaluation, which is we have validation set assesses using metric like precision, recall, and mean average precision map. Then we have performance tuning, which is fine-tune hyperparameters based on evaluation result. And lastly, we have testing. After achieving satisfactory validation performance, the model was prepared for deployment, including exporting the trained model and setting up an inference pipeline for real-time weapon detection.
Okay, so I will explain about the dataset. So the dataset we obtained is from the Kaggle, which include images of various weapons such as knife, rifles, and pistols. It is divided into training and validation sets. So the key files are that we have created train folders that contains the training image that we have done through the label img, and the validation folder that will contains the validation of the images. Classes.txt is automatically created after we have done the label img or labeling process, which has the list the classes of weapons included in the dataset, and weapons.yaml is the configuration file specifying the dataset structure and classes. So result and discussion. Let's discuss the confusion metric first. So after we have done the training, the system automatically created these two images or to the confusion metrics for us. So the one on the right side is the normal one, and on the left side is after the normalization happened. So if you can see, based on the confusion metric above, you can see that the true positive of the model is at 0.54, which is more than 50% predictability. The model misclassified weapon as background 46% of the time, has a significant area for improvement. So using the model YOLOv8M as our base model, average and balanced output are within the expectation. And this is another graph called precision confidence curve. So if you can see through the image here, so the precision of a model is the percentage of real positive detections among all positive predictions. The graph shows that in this case, precision climbs with the confidence of threshold and peaks at a confidence level of 0.9. This peak indicates that the model is more successful in recognizing true positive with fewer false positive as the confidence levels are greater. So the last graph is the recall confidence graph. So recall quantifies the percentage of genuine positive that were found. The recall of the model tends to decline as the confidence criterion rises. This inverse relationship shows that whereas greater confidence threshold increase memory, they can also increase precision. To maximize the model's overall performance, this trade-off must be balanced. Another graph is the F1 confidence curve. So the F1 score provides a balanced perspective of both measures and is calculated as the harmonic mean of recall and precision. The ideal trade-off between precision and recall is indicated by the F1 confidence curve, which peaks at a confidence level of 0.6. The model maintains an acceptable level of recall and precision at this threshold by achieving a harmonious trade-off.
For the conclusion of our project, the implementation of YOLOv8 model for weapon detection has shown promising results, with the model achieving high accuracy and speed. This project demonstrates the potential of using advanced object detection model to enhance security measures in public spaces. Future work could involve further optimizing the model and expanding the dataset to include more variation of weapon and environment. That's all from us. Thank you for lending your ears.